So welcome to today's e-showcase. Magnetic flow meters contribute to water loss when water wells are high in iron and when chemicals are injected. Before we begin, I would like to thank our sponsor, FLEXIM. Today's presenter is John Van Nostrand, and he is the Water Industry Manager at FLEXIM Americas Corporation. John brings 31 years of industry experience in various roles, including service, sales, marketing, and management. And we hope to keep you engaged during today's e-showcase. And with that being said, I will pass it over to John.
Thank you, Dylan. Give me 1 second here. Going to Dylan, please refresh my memory of where those notes were.
Those are in the bottom right corner by the chat function.
The 3 dots, right?
Yes, sir.
For a second there, I didn't see them. I think when you shared it, then I was able to. Okay, thank you, everyone. We'll begin. I'm John Van Nostrand with FLEXIM Americas. I'm the Water Market Manager and have been with FLEXIM for about 13 years. Prior to that, I was with Endress & Hauser, and prior to that, I was with a rep firm and have a lot of experience and knowledge with practical applications. So I'd like to be a resource for you, and I hope that we can pique your interest here and engage in a good conversation. So we'll jump right in with the agenda, where we'll talk a little bit about FLEXIM, and the goal of this presentation is to facilitate recent developments in ultrasonic flow measurement from FLEXIM and familiarize you with the reason why FLEXIM might be the best choice for meter installations, and especially retrofits in water applications as well as wastewater applications. I'll go through a little bit about the company, the theory behind the measurement, the meters that are used, and some successful measurement that we've done in recent past. So FLEXIM Americas is a wholly owned subsidiary of FLEXIM GmbH, shown on the left. FLEXIM Americas is based in Edgewood, New York. This is a 20,000 square foot facility there on the right, where you see in the picture. This is FLEXIM Americas, and there we have sales, marketing, R&D, production, calibration services as well. We have offices based in Illinois, California, and also in Houston. FLEXIM manufactures a number of different meters. The 4 series and the 6 series are portable flow meters that can be carried out into the field to spot check temporary service and verification of calibration of other meters, as well as semi-permanent installations. The permanent meters are the 5 series and the 7 series, and then there's an 8 series, which is a class 1 Div 1 meter. It's not often used in water wastewater applications, but I bring it up because there are sometimes in pump stations where there might be VOCs present, and that requirement could be there. So training and knowledge is important, and at FLEXIM, we're dedicated to sharing that knowledge in a number of ways, similar to what we're doing today. We do webinars, individual trainings, conferences, and specific trainings for your team as needed. Let's jump into how these meters work. Transit time meters, as the name implies, measures the difference in time travel between the ultrasonic pulses transmitted in one direction with the flow and against the flow. And we're measuring the time difference between the two, shown here. The top sinusoidal waveform is the energy traveling from the upstream transducer to the downstream transducer, and the bottom sinusoidal waveform is the energy traveling back. It's the difference in time between the two that we're measuring, and that is proportional to the velocity of the media. We know the diameter of the pipe, so therefore we calculate volumetric flow. So as far as flow measurement goes, we're measuring velocity just like any other type of flow meter and calculating volumetric flow based on the area of the pipe. We're just doing it with a transit time signal. The 721 is the meter of choice for water applications and wastewater applications. It's sold as a package, meaning that there's one part number that includes the meter, the transducers, which can be, and the tracks, the mounting hardware. Everything that you need for the meter is included in that part number. So there are a number of factors that have been helping FLEXIM become very successful, and these are the things that FLEXIM has designed into the offer that no one else does. So we're not Basically, what I'm going to talk about is what sets FLEXIM apart from other manufacturers. For example, the use of a coupling compound rather than a coupling pad or a coupling grease. So this means that there's no maintenance, and we'll talk a little bit more about that. We calibrate every pair of transducers that leave the factory. This means that you don't have to obtain zero flow or do a field calibration when you install. We match the transducers, the crystals inside the transducers so that we ensure that we have a tight accuracy before we even send them to calibration, which we do on every pair of transducers and every meter that we ship. We calibrate that meter and transducer and you get a certificate. We integrate the mounting cables, so it's a robust mounting solution. There's no guessing as to which is the upstream, downstream, etc. And then we offer a variety of techniques for measuring, like lamb wave, shear wave, which we'll talk a little bit about that too. And then again, we also temperature compensate every pair of transducers, and I'm going to talk a lot more about why that's important. So let's jump right in. First of all, the coupling pad. So we have zero maintenance once you install it. And the reason for that is that we use a coupling pad rather than a traditional grease. So if you've ever used ultrasonics before, you know you use like a grease on the face of the transducer. And over time, that grease actually goes away. It washes out or it gets crusty. The coupling pad doesn't do that. This is an up-close picture of what it looks like. I typically use just a slight bead of grease there on the coupling pad behind it in order to hold it in place so you can slide it right into the track. And that's what makes it maintenance free. Also the calibration. We calibrate every pair of transducers and every meter before we ship them. And they come with a NIST traceable certificate that is in adherence to the 17025 standard. And that's, like I said, it's a NIST traceable. So there's no need to set zero in the field. You have accuracy of plus or minus 1% of the flow rate. And the spec for repeatability is 0.15%. So you get a very accurate flow measurement right out of the box that you don't have to tamper with. So we have FLEXIM. I mentioned we match the piezoelectric crystals, and this provides us the tightest accuracy possible before they even go to the calibration rig. So this is, again, something that a lot of other manufacturers don't do. We integrate the cables into the mounting, so it's a robust mounting solution and industrial hardened, and it lasts for years. So there's, again, no delicate contacts that are made from the cable to the transducer that could leak. Everything is completely sealed. You can see here on the lower right-hand corner, that's what our transducer cable looks like into the transducer. Then we also put a mark on the top of them. So when you put those together, you see the arrow goes in the direction of the flow. So there's no guesswork as to which way you install the transducers. You know which is the upstream and which is the downstream. FLEXIM offers lamb wave and shear wave transducers. This means that you can be sure to measure accurately on liquids or gases. So we do liquids, gases, even steam measurement with our technology. And the reason that we're able to do all of that is because we have the right transducer for the application. FLEXIM uses an embedded RTD inside the transducer block, and this is an actual RTD, not a thermistor. It's not part of the measurement process. It's installed there to temperature compensate for any what would show up as drift in the measurement from the temperature of the transducer blocks changing. Imagine if this transducer pair were mounted on a large pipe and one was facing the east and the other one was facing west rather than top and bottom, east and west we're looking at. The sun comes up in the morning and it's beating down on the upstream transducer, and then as the day goes on, the sun goes to the other side of the pipe. On the west side of the pipe is the downstream. That change in temperature between those two transducers creates drift in the measurement. And FLEXIM has engineered the drift out of the measurement by adding that temperature compensation. And by the way, that temperature compensation is called out in ASME MFC 5M as a standard. FLEXIM meets that standard where other clamp-on meters don't offer it whatsoever. They don't even talk about it. So it's really important. So when it comes to Snell's law, temperature becomes very important. What we're really looking at is the beam angle, which is the Y dimension here. And that beam angle changes with temperature. So the placement of the transducers can also require a different spot as the temperature changes throughout the day, which is why often other clamp-on meters lose their signal. So we did a quick test. We wanted to prove that this was true, and we basically put our meter on a capped piece of pipe with another set of transducers from another leading manufacturer on that same piece of pipe. And what you're seeing here is an overnight test of the blue line showing the zero output from the FLEXIM meter. The magenta line is the output from a competitor's meter, and the brown line is the temperature change over the test. And we're only looking at about maybe a degree or two of change, but look at the output from the competitor's meter from the FLEXIM meter. So we took that a little bit further, and we just decided that we're going to do some laboratory testing. And what we've done here is we've done a temperature stability test in a controlled environment with an oven and two other major competitors that we value as competition. Taking a look at the FLEXIM meter over time, what we're looking at is a temperature change from 40 to 113 degrees Fahrenheit. This is a typical summer or fall day in Florida. It could get quite hot in the afternoon and could cool off in the evening, or any part of the country. And what we're looking at here is that blue line being the output from the meter. The red line is the temperature change, and that temperature changes, like I said, from 40 to 113 degrees. And then the green line is the sound speed of the media. We also know that that changes along with temperature, and we track that. And it's important to note that because we'll talk a little bit more about that in a moment. A major competitor here, what we're seeing is drift over that same test, and that is 0.07 feet per second. And let's just say on a 6-inch pipe, what does that equate to? It's about 6 gallons a minute. So there's 6 gallons a minute drift built into that meter at zero when you're just sitting on the pipe. And taking a look at another manufacturer, we see a very similar result. That's 0.1 foot per second drift. That's 9 gallons a minute on a 6-inch pipe. Now imagine that on a 60-inch pipe, and you're trying to track leaks in the water system. You're basically inducing error. With the FLEXIM meter, you don't. So another amazing technology difference with the FLEXIM clamp-on meters is the digital signal processing. And here's a leading brand's method. They digitally impose that marker. Remember I said we look for our signal, we send it, and we receive it. How do we know when it arrives? We put digital marks on it. Our competitor uses one major digital mark, and they send it through what they call a zero crossover, and then there is a detection window where that signal is being looked for as it arrives. But what happens is when the temperature changes of those transducers or the process changes, that actually can find its way outside of that box, because what it normally does is it seeks the highest peak-to-peak value on the sinusoidal waveform, and it places itself in that spot. When that sinusoidal waveform changes, so does the digital mark, and it can actually find its way out of their detection window. So what we do at FLEXIM is we encompass the entire sinusoidal waveform in our signal envelope, and we digitize it multiple times. So instead of putting one digital mark, we put 8 digital marks on every sinusoidal waveform. So if you had, depending on the frequency of the transducer, it could be anywhere from 80 to 200 of these digital marks, and we're counting them all. So now not only do we have a detection for signal, meaning that if you send 100 pulses and you receive 50 of them, you have 50% signal strength. That's pretty easy. But we're doing the same thing, but we're also measuring the fidelity of the wave. So we have a quality measurement as well. So we can actually operate with low signal and have a very good quality signal. And an example, when would you see that? Maybe on sludge lines, ductile iron pipe with cement liner, or precast concrete pipe. We're able to do those applications where other competitors can't for this reason. So AWWA is the handbook for water resource management. We at FLEXIM are very familiar with it. In fact, I'm on the committee for C75019. It's going through a rewrite right now, and the goal is to ensure that temperature compensation becomes a big part of it, as well as advanced meter verification, which we're going to talk about again in a moment here. The C715 addresses the requirements for revenue generating meters. Again, FLEXIM is fully compliant, as well as the M36 for which we're very familiar with for your water resource management program. So our calibration rig at the factory in New York can use one of two methods for calibration: the conventional method using a master meter in comparison with water in a flow loop to compare the device under test to a standard meter. And then there's also a method called the aperture calibration method, and that's a new calibration method that is used for ultrasonics. And as I mentioned, the conventional calibration is a comparison of a device under test with a reference instrument in the wet flow. However, with flow profile becoming very important, what we're doing here is we're actually putting the transducers in a wet bath and slightly moving them very precisely to essentially what we do is we simulate the flow velocity by moving them very slightly. And this is done with a laser alignment tool. And it's very accurate, and it's accepted as a calibration methodology in many industries, including the water industry. AWWA does recognize it. The nuclear power industry also likes it very much, so much that they've actually purchased some of our calibration rigs. So FLEXIM transmitter undergoes calibration as well, and it's an electronic calibration. It's carried out to like the 10th digit, so it's very accurate. So the transmitter itself, as well as the transducers, each receive their own calibration certificate. And what that means is now that you're able to take those transducers and put them into any meter along with the sense prom. The sense prom follows the transducer. That is where the calibration resides for the transducer. So you plug that into the meter. Now those transducers are mated with that meter. And if you ever need to send them back for calibration or change them out or move or replace the meter head or whatever, you don't have to replace the meter and the transducers. And they're not required to be working together. They're actually independent of each other. And once you plug that sense prom in, they become mated. So it's a really nice feature. So the question often comes up about straight runs. How many straight runs are necessary? Well, the recommendation for direct mount transducers opposite sides of the pipe is 5 diameters downstream and 10 diameters upstream of an elbow. So many piping systems don't allow for 15 diameters of straight run. So FLEXIM has performed some independent testing, which reflect mounting gives an average. And what we're doing here when I say reflector direct is I mean whether the transducers are on opposite sides of the pipe measuring directly across, or in reflect, meaning that we're sending the sound wave from one transducer on the same side of the pipe and reflecting off the back wall of the pipe to the downstream transducer that's next to the upstream transducer. I hope that makes sense. But essentially what I'm saying here is we're on the same side of the pipe versus opposite side of the pipe shooting directly across. And when we put them in reflect mount, we can shorten that installation requirement. So how much can we shorten it? Well, we've done a lot of testing over the years, and we've learned that flow profiles, how they behave, and what happens with the introduction of upstream disturbances. And as a result, we have a new feature called profile correction. And you can actually program the the distance between the elbow to the center of the transducer and correct for the profile disturbance upstream, like an elbow or a 45. So now we don't have to worry about the straight run requirements. We can install in very tight locations. So we also offer a feature called Noise Trek, and Noise Trek is a Doppler technique that works by sending a beam of energy that's tuned to a precise frequency through the wall of the pipe, and it's looking for something to bounce off of. a particle in the water, for example. It works well if there's aeration in the water or if there's bubbles in the water. Normally, we don't use the noise track feature. In water applications, we very seldom need it. The only time I've ever run into needing it in a water application is in a pumping scenario where we're pumping from a large pipe into a smaller manifold, creating cavitation, and there was a lot of aeration in the line. So then we would switch into that mode. What's nice about this is that we can switch back and forth. So we actually have a program in our meter that says, all right, if you get aeration or solids or something like that, switch to the noise track mode and then look for that transit time signal. And when it's present, switch back to transit time. Now, why do we care if we're in transit time or in Doppler? Transit time is more reliable. So we're looking at a 1% meter with that transit time method. If we go to noise track, we could be looking at a 3% meter. So we obviously want it to be as accurate as possible, so we want to remain in transit time as much as we can. So the 721 meter, it's suitable for water wastewater applications, and it's available with multiple transducers, like I said, for pipe diameters above 2 inches. We have another meter that we can measure down to a half an inch, which we do often when it comes to chemical dosing and so on. Chemical dosing is really important in water market. We know this, and because we're actually measuring about 8 times per second, we can handle the pulsations. So not to worry if you have a pulsating pump or peristaltic pump or a diaphragm metering pump or something like that. We can still measure your polymers and your hypochlorite and so on. The portable meters are excellent too. They're terrific when it comes to doing calibration of other meters like Magmeters in the field. A lot of rural water districts use these to go out and do their circuit riders go out and do verification and calibration of Magmeters. And a lot of private companies that do that also use our meters because of the reliability. You got 2 channels that you can select from, channel A, channel B. So you can do 2 different pipes, or you can do 1 pipe with 2 sets of transducers and average them and even improve that accuracy. And there's also an optional thickness gauge, so we can measure the wall thickness of the pipe, and that becomes important. We'll talk about why in a moment. We also have multiple outputs and data logging capability. All the software and everything that you need to make the meter work is in that box. That's a nice feature as well. So I have a slide here that's supposed to be animated that shows us something that's not showing us. And on the WebEx, I'm not sure how to get back to it. But essentially behind this graph, we are showing a picture of a pipe and why we are measuring through ductile iron as well as through a concrete liner. And the question also comes up is, how do you know that you've installed the meter correctly? Well, when you look at ductile iron pipe, which is very common in the water market, as we know, there are a variety of thickness classes. And if you're looking at from class 50 to class 56, how do we know that we're on the right pipe or we have it programmed correctly? I mean, for example, on a 16-inch class 50, you have a wall thickness of 0.34, where on a 56-inch, or class 56 rather, it's a 0.52. So what do we put in? I usually start right in the middle. I would go with the 0.43, and then I look at the sound speed of the media. Remember, I said the sound speed is what we're measuring, and we know that water at 70 degrees has a sound speed of about 1,490 meters per second. I look at that sound speed, and if it's not correct, I can back out of the wall thicknesses or go deeper into the wall thicknesses to ensure that I've got the right wall thickness programmed. I mean, I don't know anybody that goes on a ductile iron pipe and knows exactly what class it is. It's not marked. So you got what you have, and you don't really necessarily know. With this meter, you can actually back into it and you'll know. So with that sound speed measurement as well, remember I said about 1470 is 70 degree Fahrenheit. So what we can actually do is we can actually take a measurement of the water when we install the meter, and then we can put an output on that sound speed measurement to give us the temperature of the water. So it's accurate within the range of water systems. It's accurate to about plus or minus 1 degree. I don't know if it's important to anybody, but there are times when you might want to actually measure the temperature, especially if you're doing chloramines and you have a bio outbreak. It might change the temperature. That's becoming kind of an issue, or at least a parameter that people weren't interested in. And so I thought I'd mention it. So this matrix shows the differences between the meters of the water, wastewater applications that we most commonly do. So we have a variety of meters that we can choose from with a variety of features, but all come completely with everything you need in the box. And we typically use the PermaRail mounting track system. So this is a robust mounting system rather than just strapping a transducer on the pipe. Another thing that's important is the advanced meter verification. So what this does is this gives us a report of how the meter was when we installed it. We look at a lot of diagnostics and it saves this in the historian. And then when we come back to the meter, let's say at an annual calibration interval, we can actually look at those diagnostic values and we can see if anything has changed, if any trends have occurred or signal losses, etc. And then we have on our report an indication in green, yellow, or red to say that it's good, it needs to be attended to, or it has some kind of a malfunction. We also use something called a virtual technician. And what the virtual technician is nothing more than a tablet that is a tool that you can go out in the field. And essentially what this does is this allows the maintenance personnel to go out without IT involvement, plug into the meter, and then if you have a hot spot, our technician can actually dial in with you and help any diagnostics, help with the advanced meter verification, with the parameterization of the meter, the setup, the commissioning, etc. So it's a really nice little powerful tool. So let's jump into the water loss and why it's important. You know, there's growing political pressure to reduce water loss. We all know this. It's kind of gone from being a headache to a migraine. And there's competition a lot of times between utility companies and municipalities to be the best at resource management. And those who fall below the standard ranking may be considered poorly managed. They may face pressure from governing authorities to improve, and water loss reduction is really being put in terms of dollars and cents rather than percentages of the inlet and the distribution. So let's first talk about regulation. We know the lead and copper rule originally started as an initiative in 1991. It was intended to encourage putting anti-corrosion additives into drinking water that coat the insides of the pipes to prevent metals from leaching into the drinking water. Well, today that rule has become a requirement, and now all utilities that serve more than 50,000 people, and that's about 68,000 public utilities in the U.S., have action level requirements. In other words, if there's an action level of 10 to 15 parts per billion, then they must do something to curb that lead leaching and copper leaching into the water. So it becomes really important. And then what happens is, you'll wind up injecting orthophosphate into the water, and injecting chemicals have unintended consequences on magmeters. The coating fouls the electrodes and basically renders the magmeter useless. So what we're seeing here is a study that we had done at a well over a period of time, this is nearly 2 years, where the FLEXIM meter was installed right next to a leading manufacturer of magnetic flow meters. And over time, in this case, manganese coated the inside of the pipe. Orthophosphate and manganese have the exact same effect on magnetic flow meters. They basically, well, I shouldn't say that. One actually coats the electrodes so that the electrode signal cannot be detected and they can't feel the water, essentially, while the other one creates a direct short. But the end result is they start out reading properly, and over time they read lower and lower until they just fail. And magnetite is the reason for this. And magnetite is a mineral that is most common on the planet. It's a rock material, and it has iron in it, and it's ferromagnetic. So it's attracted to a magnet and can actually become magnetized and permanently sticking to itself. If you look at it under a magnifying glass, this is what it looks like, this lower right-hand corner picture. And to me, it looks an awful lot like ceramic, except usually that's aluminum oxide, and that's usually white material. In this case, it's iron oxide, and it's a black material. And each of these little specks of iron oxide have a north and a south pole. So what happens with this magnetite is it actually coats the inside of a magmeter, creating a short between the electrodes. So when we look at how a magnetic flow meter works, we have electrodes. It works on the principle of Faraday's law. There are electrodes on both sides of the meter, and then there are coils around the other opposite sides. So we're basically inducing a magnetic field. And what Faraday's law states is that if you have a magnetic field and you pass a conductive material through it, it will output a voltage that's directly proportional to the velocity of that media. So there again, they're measuring the velocity of the media by picking up the voltage output that's a result of the induction that's being done by the magnetic field. And they're measuring that velocity and calculating volumetric flow based on the area of the pipe. But as the name implies, magnetic flow meter, you're creating a magnetic field and then sending a magnetic material through it. It sticks to it like glue. And again, that material builds up and it creates a bridge from one electrode to the other, creating a direct short. So over time, it'll read properly and then read lower and lower and lower. So that is a real issue. And magmeters like velocities between 3 and 33 feet per second. So turn down becomes an issue. And the turn down refers to the operational range of the device, and it's defined as the ratio of the maximum capacity to the minimum capacity of the meter's ability to measure. So off-peak times, you'll see very low flows and you'll see very large discrepancies. So the other thing I'd like to point out is that we assist a lot of water utilities, and then we've learned that most drinking water piping systems flow below 3 feet per second. Why is 3 feet per second important? Because again, that's where the magmeter starts to perform the best. Will it read below 3 feet per second? Sure. But it drops off the accuracy. And not all manufacturers are the same. Some are worse than others. And you'll get very low flows. And we see off-peak times the flow diminishes to velocities below 0.26 feet per second. Sometimes it even flows backwards. And with low flows like these, it's nearly impossible for conventional meters to capture the movement of the water. So why below 3 feet per second? Like I said, that's the sweet spot for a mag. This is a particular calibration curve. So if you couple that with lead and copper, any injection of orthophosphates make this really exacerbate this. So this is from the flow rig what the calibration curve looks like. And again, you see about 0.3 feet per second. You can see that you're getting up to about 2.5% versus the 0.5% that they advertise. That 0.5% is, like I said, is ideal conditions from 3 to 33 feet per second. Most water systems flow below that. What's important to note is that the velocity that FLEXIM is able to capture goes down to 0.03 feet per second. So it's essentially 100 times less than the sweet spot for a magmeter. Hard to believe, but it's been proven over and over, and we continue to have great success with it. Here is a picture of just a typical verification of calibration check. Look at the straight run here. There's very, very little. Again, we have the capability to dial in exactly the distance between the flange to the center point of the transducers, and we can offset any disturbances upstream from the transducers. Magmeters here, you're looking at the difference, you can see they're right on the money. 1392, 1399, they're about well within 1%. So that meter, that Magmeter, passed calibration. Another thing to consider when you're looking at a FLEXIM meter versus a Magmeter, average about $4,000 to install. I've seen it as high as $13,000. And then you look at the number of downtime hours that you're going to have. Typically about all day is what it takes to install. Unless you're in a situation where they're very large pipes, then it can take several weeks. Not to mention the lead time to get a Magmeter. So with the FLEXIM meter, we clamp right on the outside of the pipe. We don't have any downtime whatsoever. There's no calibration that you need to do. You zero it at the factory. Everything is calibrated, ready to go. You install it in the location, set it up with the proper wall thickness and diameter, and we know that we've got that correct based on the sound speed measurement. You're off and running. We've helped a lot of utility references. These are some around the country. It's not a complete list. It's just a kind of a shower of municipal customers all over the country that we've been able to assist. We measure polymer. Polymer dosing can be done very accurately with the FLEXIM meter. We have a lot of applications where, this is obviously polymers primarily used in wastewater applications. But again, because we're able to measure multiple times per second, we can handle those pulsating flows and the high viscosity. We have Reynolds number and viscosity compensation built into our meters. So we get very accurate results measuring polymer. Here's a drinking water production well. This is a 12-inch stainless steel well. We've got the CDM transducers. This is a well that is full and heavy manganese. So the Magmeter failed. There was a Magmeter on this location. Over time, it just failed, and they would have to take it out. It's a 12-inch pipe. They would have to take it out, reach inside, clean it with acetic acid, basically a vinegar solution, put it back in service, and it would work again. But the utility was like, I can't drive around with a crew doing maintenance on these Magmeters, so that we installed the FLEXIM. So underground installations become tricky, and there are often times where you might need to put a meter in, but you don't have the ability to install a vault. So we'll bury them directly in the ground, and we'll basically prepare the transducers so that they're not going to move. We'll test the application. We know everything's working well before we backfill. Now, again, we don't necessarily like to do that, but we certainly can. This is an interesting story. This was North Texas Municipal Water District, where they had old Fisher Porter Magmeters on these cement pipes. These are 60-inch diameter pipes. And they were looking at having to remove the roof of this building, cut these lines, shut the plant down. This was going to be millions of dollars to install 6 meters in weeks of downtime. We said, look, let's give it a try. We went out there, we installed the meter, and essentially what we did here is we used a Bondo filler like you would buy from an auto parts store, and smoothed the pipe and installed our transducers, and we got accurate flow measurements before lunch. So our technicians were in and out of this location by lunchtime, and the customer is extremely happy. In fact, there are other utilities that use concrete pipes that have been to that site and visited, and as a result have placed orders for meters on their systems. This is a typical pump station for sewage collection. It was a new construction project, and I like to share this because this utility in particular does not use Magmeters at all anymore. They've completely switched to FLEXIM, and they've had very good success. They've reduced their water loss numbers, and they've improved their plant process, as well as now using them on the wastewater side for sewage collection. This utility is in the Northeast. It's a very old infrastructure that dates back to 1857. This is an interconnect from Greenwich, Connecticut to a utility in New York State where they're selling water to them. It's a 16-inch ductile iron with cement liner, and the company was using a turbine meter for billing, and they were missing revenue during off-peak times due to low flows that the meter was not able to capture. And because of the need of greater accuracy, we actually use two sets of transducers and we're averaging them. And the customer has been extremely happy with the result, and they actually improved their revenue. In this particular case, a customer installed a magnetic flow meter to ensure the proper dosing of sodium hypochlorite. The magnetic flow meter didn't stand a chance during off-peak times because the flow was so low. I mean, look at this system here. They've got looks like one Stenner pump moving sodium hypochlorite through a 1-inch line, and take a look at what that flow meter says, 0 flow. But in actuality, there was 2.8 gallons per hour, which is 0.13 feet per second. No chance a Magmeter is going to read that. So remember I said our load detection limit is 0.03. Well, we're at 0.013. So we're actually below our standard accuracy. We're essentially our range, but we're still able to measure. So measurement is better than no measurement for sure. Are we extremely accurate below our low limit detection? Our accuracy has that bell curve just like the Magmeter, but the point here is we're 100 times lower than 3 feet per second. So these are larger. This is a pump station at a major utility that could not turn this flow off. It's a 36-inch carbon steel pipe, and there's 20 million gallons a day of raw sewage that flows through the station. They'd like to know the number of gallons, but they could not turn it off. To install a Magmeter would be a massive undertaking here. So we actually went and did a demonstration and proved to the customer that we're getting accurate flow measurement, and they were very happy with it, and they've installed this in a permanent installation, and now you see that it just remains underwater. So we have IP68 capability, and that customer has been very happy. This is an actual, Venturi meter, but it's in a wastewater stream. You don't necessarily see that very often. It's a mixed liquor application, but needless to say, the impulse lines were plugging on this transmitter. So FLEXIM offered a very easy transition to install a meter, and they just abandoned that Venturi altogether, using the power from that DP transmitter to our meter and using the same signal wire. Again, we were in and out of there in no time, and the customer is extremely happy. Now, the question has come up, can we do pre-stressed concrete pipe? The answer is yes. Take a look at what is involved with pre-stressed concrete pipe. We've got our first pour, then we've got a steel cylinder, then we've got a second pour, and then we've got pre-stressed wires. Now, this is just not, a lot of people think of this as rebar. It's not rebar. It's actually loaded tensiled wire. And it is the size of rebar, but it's springy inside. And then another pour on the outside of that. So this can be as much as 7 or 8 inches thick with concrete and steel. And we've actually done our homework on what the sound speed measurement should be through this pipe. And we programmed that in, and we actually have a file for that. This is a very common installation for water systems with concrete pipe. You'll wind up having to tap the pipe and insert a Magmeter. It's a point velocity measurement. What I mean by that is a single point where they're measuring in the velocity stream. They also have averaging style Magmeters where they might average a number of points along with multiple sensors in order to improve their accuracy. But the point is, these meters are problematic. They really degrade the integrity of the pipe when you start drilling into the concrete pipe and so on. So you no longer have to do that. So what we do is there's a number of ways we can install these. We can actually epoxy them directly onto the concrete pipe, or we can strap around the pipe if we're able to get around the pipe. And then this is down inside the vault, and this is what the meter looks like just outside the vault. Orange County Sanitation District, this is another concrete pipe, and I'm really focusing on concrete pipe for this application because when you think about it, you install a Magmeter in a concrete pipe, you're going to use that insert style. They're not very accurate, they're not very reliable, and if you install a full bore Magmeter, you're looking at some serious costs. And what I'm asking you to do is have a look at FLEXIM, and we can do a feasibility test with it very, very quickly to go out and do an install and demonstrate the meter. And we can then determine, and there's no cost to you to do that. And we can then determine that it's a good application. But this particular Orange County Sanitation District, I'll be out that direction in 2 weeks in Southern California. This is a 90-inch concrete pipe. Unheard of for clamp on, but we're able to do it. Here's another one, other side of the country. This is Miami-Dade. This is the North Beach Wastewater Treatment Plant. And in Florida, and you might have heard about this, but we're going to a zero discharge in the state of Florida. And other states will most likely follow. And what I mean by that is that no effluent from wastewater treatment plants will be allowed to go to open waterways. So there's no longer going to be any dumping to the river or effluent going to the ocean. This particular line is a 60-inch. I think it was a 60-inch. That's me standing up on the top, by the way, looking down in the hole. They have to measure this because this is their overflow after the deep well. So if they're unable to keep up with the flow going into the deep well, which is about 1,800 feet into the ground, then they'll use the old discharge going to Biscayne Bay through this large pipe. And to install a Magmeter in this would have been a huge undertaking. And we were able to clamp our transducers on the outside just using a strap. This is a portable meter. And you see our technician here. He's very happy about the installation. And Miami-Dade is very happy about the installation as well. I love to share this story. I know we're almost out of time. I've only got a couple of seconds left and we're at the end. So this particular case, in this particular case, we had East Burlington, North Carolina. They had a basin and a metering vault next to the basin at the wastewater treatment plant. And they have a full bore Magmeter installed down there. This is what it looks like from the top. And you can see, here's the Magmeter. The flow is going from the top of the picture to the bottom. And there are transducers on the pipe. And so what we did is we went down there and we installed the transducers, and the flow measurement was 0.01 feet per second. I mean, very, very low flows. The flow volume is about 5 gallons per minute. And what this does is they had the Magmeter that was installed on this line, and they have to open a valve in this vault during heavy rain events. And when that rain occurs, if they open that valve too much, it can create a suction and it will actually empty the basin. And so they cannot open it more than 14% open. Otherwise, that siphon will occur. So when you look at the span of the meter, the set point is at 14% of the valve. That Magmeter, that's only about 22 gallons per minute. That Magmeter would only begin to read at 15 gallons a minute. Look at where the FLEXIM meter began reading. Almost, less than 5 gallons a minute. So it's amazing that the customer was able to get that much more range out of his system and have that much tighter control of that valve position using the FLEXIM meter over a leading brand Magmeter. So that's a very powerful illustration of the capability of FLEXIM. And with that, I'd like to open it up to any questions and we can have a quick discussion.
Great. So we have one question from the audience. And they want to know how long does it take for manganese to coat the inside of a magmeter?
Yeah, so manganese, depending on the concentration of the manganese, it could be anywhere from 3 months to a year. I think an average is about 6 months for the meter to become affected by it. And what I mean by that is, begin to lose accuracy and over time, and immediately it will lose the ability to capture very low flows. That's the first thing to go. And then over time, it just builds up more and more until it can't read at all. And it's not that the meter has necessarily failed, but it's fouled up on the inside. So you have to do maintenance. In other words, you have to go remove that meter. And by the way, electrode cleaning circuits are powerless against manganese. It's an organic material, iron material that coats the inside, and changing the polarity of the sensors or the electrodes and burning it off doesn't affect it. So once it happens, it has to be dealt with physically. Good question. Thank you.
Awesome. And we have enough time for one more question. Right? Um, an audience member wants to know how many points of the signal are processed by FLEXIM UFMs.
Yeah, so how many points of the signal? I think I might need clarification on that question, but what I can tell you, and I think I know what you're getting at, is that we're averaging 8 times a second we're sending that signal. Again, depending on the frequency of the transducer, but let's just say most applications we're looking at 8 times per second, and then we're reporting every 1 second. So of those 8 measurements, we're reporting the average 1 second intervals. Good question.
Great. Well, I want to take this time to thank you, John, for a great presentation, and another thank you to FLEXIM for sponsoring today's event. This concludes today's e-showcase, and I thank you all for attending. The recording will be available at wefbuyersguide.wef.org, and we'll send our registrants an email tomorrow with that link. Please visit our event calendar to sign up for future events, and have an awesome day.
Thank you, Dylan.
Thank you.